Alright, so this is going to be a video about how limits and continuity are related. And basically how they are related is this equation right here. What's highlighted yellow right there, it says that the limit from one side has to be equal to the limit of the other side, which has to be equal to f of c, which is when you actually plug in that value. So this states that at a point c, in order for it to be continuous at c, this all has to be true. I'm going to draw an example later to kind of explain this a little bit better, but just know that this is the definition of continuity using limits. Now, based on this definition of continuity, there are types of discontinuity that are based off of certain things in the definition that are missing. The first type of discontinuity that we're going to talk about is called removable discontinuity, and this basically involves anything with holes. This first bullet point right here, where it says f of c is not equal to the limit, so this part right here, where it says f of c is not equal to the limit of f of x as x approaches c. Basically, that is disproving this whole part of continuity. But the one thing that is still accurate for this removable discontinuity is this part right here. So this part is still true. It's just this part is not true. And this is only for removable discontinuities. So that's kind of why I was using orange there. Okay, so I kind of wrote that in the second part right here, the second bullet point, that the limit of f of x exists. So that's why this first part here is still true. It's just this part that wouldn't be. This is only for removable discontinuity. For non-removable discontinuity, this involves jumps, gaps, or asymptotes. This is what basically happens when the limit of f of x as x approaches c does not exist, and that's what it says right here. Now going back to our definition of continuity, it's saying that this first part right here is not true, so it's not equal. So these two things basically right here, this and this part of the limit and this part of the limit would not be equal. So this is trying to draw a not equal sign here. So these would be not equal. So that's for non-removable discontinuity. And then I have a graph right here that kind of shows an example of both of them. So at this part right here, I'm going to call this x equals a. This would represent a removable discontinuity. That's why I colored it orange, because the limit agrees on both sides. So if I had little arrows here, it's showing that the limit agrees on both sides, but it's not actually equal to f of c, because f of c is this little island down here. This would be actually it would be f of a in this case. Now it's not equal to the limit as x approaches a from both sides, because this value right here is different than this value right here. So that's basically the removable discontinuity example. A non-removable would be occurring right here. So let's just say this is when x is equal to b. And as you can see, the limit from this side does not match the limit from this side. And if you remember, that's based on our what makes something a non-removable discontinuity. It says the limit, this part right here, the limit of f of x as x approaches c does not exist. Now we used b in this example, but the same premise still holds. So that's limits and continuity. If you have any questions about anything in this video, let me know.